Hello, everyone. Thank you for your patience. We're going to get started. So thank you all for joining us. My name is Jana Bruda. I'm the Director of Events at HashiCorp. We're really thrilled to have this webinar today. Today's webinar will include a presentation from Brandon Chavez. He's a Solutions Architect at Amazon Web Services, and then a presentation from Mitchell Hashimoto, our co-founder and CTO of HashiCorp. If you have any questions during the webinar, please enter them on the side panel, and folks from our team will try to answer as many as we can during the webinar. And then there's some questions that we'll assign to Mitchell and Brandon while they're presenting, and then some of those questions we'll keep to the very end, and we'll hold a Q&A. So without further ado, first up is Brandon.
Great, thanks, Jana. Hey, everyone. I'm Brandon Chavez. I'm a solutions architect with Amazon Web Services, and I work in the Amazon Partner Network, which means that I work with our technology and consulting partners that bring products and solutions to our AWS customers. So you might be wondering why AWS is here, but really what I'm here to talk about is how AWS and HashiCorp work together to bring interesting solutions to our customers that solve for their cloud computing needs. So the first thing that I want to talk about was really how fast things change at AWS. And I've been here for about 4 years, and maybe the most impressive thing has been just the constant rate of innovation. So this graph is interesting to look at. This is the amount of features that we release year over year, and this only goes to 2015, so it's even crazier this year. Basically, I work here, and I can't keep up. We have over 70 services to interact with. We're constantly adding new features to all of these services. At the time this graph was produced, we released over 2,300 new features and/or services since the inception of AWS. So basically, what this means is it's crazy to try to keep up with this rate of change, and this just kind of stresses the need for effective tooling to interact with AWS. Another important thing to think about with Amazon Web Services is that we have over 1 million customers in 190 countries. So we provide many options for global deployment. And we do that while also providing for extremely high reliability. So we currently provide 13 regions and 35 availability zones. And to kind of elaborate on that availability zone concept, an individual region will always contain at least 2 availability zones. And those AZs are on completely separate power grids and floodplains and always comprised of multiple data centers. And this is to provide redundancy within that availability zone. We don't build regions that only contain a single data center because it just wouldn't offer the reliability that our customers require to run enterprise businesses, for example. So this highly available global network allows you to deploy your applications near your customers much faster and in a simpler way than what can be achieved through a traditional model. We also give you a lot of options in how you deploy. So AWS has supported hybrid cloud deployments ever since our inception. So we found that with legacy systems, there's always going to be a period where you're in both environments. You're running on-premise and you're running in the cloud. And so we've put a lot of time and effort into making sure that your on-prem resources can really operate seamlessly with the cloud. So we've been working with enterprises since our inception in 2006 to use AWS in all manners of hybrid architectures, and we built a set of services and capabilities that really provide the broadest and deepest hybrid functionality of any cloud provider today. So we give you functionality to extend your network into AWS, ways of controlling both on-premise and AWS resources at the same time. And Terraform is a fantastic tool for our customers because whether they're all in on the cloud or in transition, Terraform provides a way of creating and managing the resources you use in AWS, as well as on-premise. So we'll dig into Terraform a little bit more, especially once Mitchell comes on. But real quick, I wanted to talk a little bit about the HashiCorp and AWS relationship and what we're doing to bring solutions to our customers. So I wanted to frame this by talking real quickly about the Amazon Partner Network, which is basically an organization inside AWS that's specifically for working with our technology and consulting partners. So we work together with these partners to build products that solve needs for our customers, and we also use the APN as a mechanism to help our customers identify which partners can help them in their specific cloud journey. All customers have individual needs, So one of the things we've done is we've built and operated this program called the Competency Program, and we use this to maintain what's basically like an all-star list of technology companies and consulting partners that are best in class. So we've got a variety of categories like life sciences or big data or DevOps in particular. And I'd recommend you take a look at these competencies if you're trying to identify a partner that could solve for a specific need on AWS. So HashiCorp is a DevOps competency partner, and that means that they offer some of the premier DevOps tools that work with AWS products. So more specifically, our DevOps competency partners provide solutions to or have deep experience working with businesses that help them do things like implement continuous integration and continuous delivery practices, or they help them automate infrastructure provisioning and management with configuration management tools in AWS. Also part of these competencies, or we ensure that these competency partners have public references, which helps us ensure that our partners have proven success in solving problems for AWS customers. And so HashiCorp is a great example of one of our DevOps competency partners. Another interesting component of the partnership is there's a huge active community of developers that use AWS and Terraform together. And I think if you look at the project on GitHub, it really reflects the amount of enthusiasm that Terraform users have for AWS and vice versa. So AWS and HashiCorp customers and just the community contribute back to the code base. And the result of this is that we see AWS features supported extremely rapidly. So despite the massive rate of change you see in the AWS platform, as we talked about a little bit ago, the Terraform community does a great job of keeping up with it. And this really ensures that Terraform can just help you keep up with the rate of change in AWS. It's fun to see all this development done in the open. The maintainers are excellent at being responsive, and it's a wonderful community. So we're excited to be a part of that. It's important to call out, though, that it's not just the community that provides the AWS integrations. So, for example, AWS and HashiCorp work together to bring a number of integrations in these products. One of which that's interesting to call out is HashiCorp Vault has a AWS-specific secret backend, which brings customers some helpful features. One of which is called Secure Introduction, in which you can automatically retrieve a Vault token by trusting AWS as a trusted third party. And you can get, essentially this uses some cryptographically signed dynamic metadata information that uniquely represents each EC2 instance, and trust that as a proof of identity, which is an awesome way of interacting with Vault. And you can also use it to generate AWS access credentials dynamically based on IAM policies. So basically you can generate policies on the fly and credentials on the fly and then automatically revoke them when the Vault lease expires. So we're working together to kind of solve some of these challenging problems across the HashiCorp suite of products. And Vault is simply the most recent and most interesting collaboration, I think. But what we want to convey here is that if there's something that you think that AWS and HashiCorp could help you resolve by working together, by all means, let us know. At AWS, we're extremely receptive to future requests. And if there's something that you need resolved and there's something that you need in order to achieve a specific use case, definitely give us that feedback, and we're always excited to hear what our customers want. And you'll also occasionally find AWS and HashiCorp collaborating on blog posts and other technical material just to help out our community. So a good example of this is earlier this year we posted a blog that's about getting started with Terraform on AWS specifically. So in this particular blog, we talked about some best practices with handling secrets, for example. So like how you can use the standard AWS credential providers. And this includes IAM roles, which is really cool. So if you run Terraform from an EC2 instance with an IAM role applied, Terraform will use it automatically, which is great. We love IAM roles. So we also in this blog post talk about some aspects of structuring your Terraform templates to logically correlate to the structure of your AWS infrastructure. We talk about how to use variables and modules. But Mitchell will probably talk about all these specifics in a little bit here. And then finally, this is maybe the latest aspect of our collaboration. We've built 2 new Quick Starts. And so Quick Start is a program that we run here at AWS to help our customers quickly deploy production-ready reference architectures. So we worked with HashiCorp to build both Consul and Vault quick starts. And we think this is great because these are two widely used HashiCorp products on AWS, and we really wanted to help our customers get up and running quickly on AWS while providing a little bit of AWS common sense, as I like to call it, built into the templates. So these are available as CloudFormation templates. They're open source, so you can either deploy them just as they are, or you can modify them and make them your own and use them as a base for your own deployments. So the Consul Quick Start can be deployed into your existing VPC, or you can let the Quick Start set up a VPC for you, and that VPC will be configured kind of with some best practices. So in this case, it deploys the VPC across multiple availability zones with both private and public subnets. And in the public subnets, we've configured some NAT gateways, and then all the Consul nodes get deployed into the private subnets. We let you configure 3, 5, or 7 Consul servers, and then as many Consul clients as you want, and they're configured in an auto-scaling group. And then the the Consul servers have EC2 auto recovery turned on, which is a nice feature in case of failure of your instance. So a lot of the heavy lifting of getting this up and running is kind of taken care of for you. And essentially, it's one click and filling out a couple of parameters, and then you have a fully running Consul cluster. And then to extend that, we've also built a Vault Quick Start. And the Vault Quick Start is built to take advantage of the Consul Quick Start, and it will use Consul as the backend. We chose that because of the integration between Vault and Consul. It provides high availability for Vault, which is great. So if you deploy the Vault Quick Start, you can actually choose to deploy the Consul Quick Start at the same time. And in the Vault Quick Start specifically, we deploy and configure 2 Vault instances, and they both have EC2 auto recovery enabled. And then we've done some of the work to set up monitoring, CloudWatch logs, pushing Vault audit logs to CloudWatch logs, for example. And then we've written a nice deployment guide to walk you through the whole process. So from spinning up the infrastructure to actually logging in and getting started with Vault, you should have a complete step to getting this running in production in your account. So go check these out. You can find a summary blog post on the Amazon Partner Network blog, and then links to all the assets from there. So finally, the last thing I want to do is just talk about a customer that's using AWS and Terraform Enterprise to provision and manage their AWS infrastructure. So Red Bull Media is a case study that we're working on right now. And excuse me, so Red Bull Media is the arm of Red Bull that provides all the live streaming TV and audio services. And they're running a fairly large deployment on AWS, between 300 and 500 instances at any given time. And so they're using Terraform Enterprise to automate and manage all of this infrastructure at once. But what moving to Terraform Enterprise enabled for them was essentially codified infrastructure that they can store in version control. And then it really helped to establish common and repeatable workflows that allow them to iterate on this infrastructure across their development teams, which is fantastic. So essentially what's happening is Red Bull Media House is able to leverage the HashiCorp ecosystem to take advantage of many of the features in AWS and improve their agility and their ability to create and manage their infrastructure all from a single source. So that's it for me. I'm actually going to pass it off to Mitchell now to dive into some of the specifics of Terraform. Thanks, everyone.
Hello, everybody. One second. All right. Okay. So I'm going to be talking about Terraform, obviously, introducing Terraform. Thanks, Brandon, for some high-level information about how HashiCorp works with AWS. So I'm going to focus today on introducing you to Terraform. If you've already used Terraform in some capacity, some of this information is probably redundant, but I really want to sort of start with just an introduction to why we built Terraform, what problems it's solving, and how you get started with it. So let's get going. So to start, I want to talk about the problem, like what inspired the creation of Terraform. And it could be represented in a couple ways. This is one way I like to look at it, which is the problem of rising data center complexity. So this diagram is one we use in a number of our talks to really represent our view of what I like to call the modern data center. And the modern data center is really, what's funny is it's called the data center, or we call it data center, but really the word data center is becoming more and more abstract. It's becoming less of a physical thing you could point at or look at, and just really representing to me the collection of all the things you need to run in order to run an application. And before it used to just be servers in the data center, but nowadays it's a lot more nebulous. So there are still data centers. Amazon in Amazon there might be regions and availability zones. Within those, there's still servers running. You're running VMs on those servers. On those VMs, you might be running containers. You might have servers that you're just running containers on directly. There's a mishmash of like a ton of different things going on there that you all have to manage. So it's pretty complex. And then at the same time, all those things communicate with other resources. So represented by these cloud icons, there's a ton of just service providers out there that run what used to be sort of core software of your data center. They run that now as a service. So things like DNS, CDNs, databases. These are things that you can now just buy basically and get full management. And obviously Amazon provides all those things. And so when you ask somebody now to spin up the sort of the minimal infrastructure needed to run your application, it's not just as easy as starting one server anymore. It usually involves starting a number of things and connecting them together. And it only gets worse as you go from minimal infrastructure necessary to real production scale infrastructure with multiple applications and multiple business units and things like that in your company. And so we wanted to build a tool to basically automate all of this for you. And one other way to look at it is this diagram here. And this diagram is just a diagram of a fairly standard vanilla web application. So you basically have a CDN in front of a load balancer, which is in front of application tiers or web server tiers, and a database, and storing some static stuff in S3. There's nothing in this diagram that's particularly, I would say, too advanced. It's obviously not super beginner level, but it's not something that only an expert should be able to do. This is a pretty standard web architecture. And so when you look at this diagram, you can see here too that if someone asks you to spin up a new web application that is more than just for development, is really that's meant to serve real traffic, and you're faced with spinning up all these resources, it could be daunting, and we wanted to automate that. So sort of in summary here, the problem really is that the data center is a complex multi-provider problem. The minimum infrastructure required for deployment is high, and manual creation just becomes too time-intensive very, very quickly. Which leads us to Terraform, which is a tool we created to solve this. So the goals of Terraform from the beginning were to unify the view of resources using code. So being able to actually code your infrastructure, no matter whether you're using ELBs or Route 53 or instances, or maybe even another provider with AWS. It was to support the modern data center, which is what I sort of just defined, but this involves all layers of infrastructure as a service, platform as a service, and software as a service. It's pretty rare today to find any reasonably sized deployment that doesn't use all three of these things. So, as an example, IaaS in Amazon is EC2. Platform as a service could be a number of things in Amazon. It could be something like Beanstalk. It could be something like OpsWorks, or it could be ECS even in some cases. And then software as a service are things like RDS and Route 53 and so on. And you're usually running all three. So you need to be able to communicate with all three. It's not enough to have a tool, for example, that just spins up virtual machines. That's not going to be enough for this use case. We also wanted a way to safely and predictably change infrastructure. So at the time before Terraform existed, when I was looking at this problem, there was a lot of tools out there that made it pretty nice to create infrastructure, but there weren't many. It was very, very rare to find a tool that stuck around as you changed your infrastructure going forward. So And even with the tools that did that, I saw a lot of people, the way they were using the tools was they completely codified how they create their infrastructure, but once it's created, they go back to normal manual modification and change. And that isn't very scalable, and so we wanted a tool that you would feel confident could safely change your infrastructure. And then we want to provide a workflow that's technology agnostic. This goes in line with multiple providers. We live in a world where a lot of your things might be on something like Amazon, but there's always one or two things that isn't. So an example for me, that I won't name any specific vendors. I don't even know if I'm allowed to, but like I use Amazon for most things, but I don't use Route 53 for DNS. I use something else for DNS, and I still want to be able to use a tool to spin up my Amazon resources and then configure the DNS with those resources, even though the DNS isn't on Amazon. And I wanted one tool to do that, so Terraform could do that. And then the final thing is a little bit more broad, forward-thinking, vision-y about the project. And what we recognize is that everything today has an API, and pretty much everything has life cycle associated with it. You create something, you update something, you destroy something. Anything with an API usually has those life cycles. So we viewed Terraform as a more abstract tool to pretty much manage anything with a lifecycle API, and that was the goal here. Terraform versus other tools, sort of in the abstract, we wanted to do better, and to do that, we aim to provide a high-level description of infrastructure. So you'll see that with the language that I'll show you shortly. We wanted to allow for sort of composition and combination of multiple providers, but also multiple levels. So one of the first demos we ever tried with Terraform 0.1, like way back, just to see if it was solving the problems we had, was a demo which created sort of on bare metal, actually created the OpenStack type installation, requested VMs from that sort of thing, installed a scheduler on top of that, and then deployed applications on top of that. So it was like a 4-level system. And the only reason we didn't use AWS for that was to just try to go as low as we can, just to see if it was possible. And it was. And so that sort of composition was really important with Terraform. The other thing is parallel execution. So Terraform parallelizes as well as it can, and ends up doing things very, very efficiently. And then the last thing was the most important thing, which I remember saying when we first created Terraform, which is if it can't do this, we might as well not create it at all, which is separating planning from execution. So the only way to get to that goal, I stated in the previous slide, of being able to trust Terraform to change your infrastructure over time is to be able to ask Terraform what it's going to do before it does it. And so Terraform supports this notion of planning, which shows you what it's going to do before it does it, so you could be confident that it's going to do the right thing. And we'll talk more about that in a second. And then finally, just before we dive into like how you use Terraform, I just want to talk about the state of Terraform. So first of all, Brandon mentioned a lot of this too, is it's open source. I'm surprised sort of how many talks I give on our tools, where at the end of the hour, people come up to me and think I just gave a talk on commercial software for the whole hour. But I want to just say that Terraform and everything I talk about here is open source, completely free. The first release was a little over 2 years ago, is in July 2014. So it's not a super old project, of course, but it's also it is also very mature. There's over 700 contributors currently, so it's very active, a very large community. Over 6,200 GitHub stars. That's a vanity metric, but even though it's a vanity metric, it's usually a pretty good measure of community acceptance of something. So take that as you will. And we average a release about every 2 weeks. So we're very, very active in shipping, and we do that very often. And just to show the power of the community, especially when we started Terraform, and Brandon again talked about this, but one of the biggest concerns we got from people was, how can a tool that aims to, control all these different providers, and not just AWS, but even just AWS, how can a third party ever keep up with them? And it really comes down to the power of community, is the fact that at HashiCorp, we have a number of people, a dozen or so, working on Terraform, but they don't even need to keep up because we have hundreds of community members. So it's sort of like having hundreds of people working on making sure Terraform supports the latest features. So we actually, since Terraform is a little over 2 years now, we went back and looked and saw sort of the average time between an announcement of an AWS feature and the pull request opening to support it is about 30 minutes. So that could be when people at HashiCorp are asleep. It doesn't need to be an official thing. Like we get a pull request really, really quickly to support new features. And also, as part of that, when there are announcements that are particularly impactful, for example, when Amazon announced application load balancers, people wanted those really, really quick. So we'll prioritize releases for special announcements just to make sure that new features are out in Terraform. So while we do average a release every 2 weeks, for example, when ALB was announced, we did a release the next day just to make sure that the community had access to manage ALB resources. Okay, so let's dive into the basics of Terraform. And to get started, I'm just going to show you sort of what Terraform looks like when you write the code to manage resources. So here's valid Terraform syntax here. This is managing an AWS instance, and as you can see, it's human readable. It's all code, and you just describe what you want. We'll jump back to that code in a second. So the goal of infrastructure as code here is to provide a codified workflow to create and manage infrastructure. You get benefits like integrating with application code workflows. So since it's code, you just treat it sort of like an application. You put it in source control management. You're able to do CI on it. You're able to do code review with it. It's not something that a person just manually does or you follow a bunch of checklists. It's actually like you see the code and how it evolves. The most important thing I think with this last point though is distribution of knowledge. So I remember in the first operations position I sort of took at a company, the process was kind of, I was hired, there was various wiki pages around of how the infrastructure worked, but they were usually outdated. So really how I ended up learning how everything worked was the more senior operations people over months and months would just slowly tell me how things work. When something failed, they'd be like, oh yeah, you haven't seen this before, this does this is how we manage it, this is how it works. And it's sort of this oral tradition of knowledge getting passed down just orally, just vocally, and it's really inefficient, and it's also prone really easily to mistakes. If somebody says, oh, this is how it works, but somebody changed it since that person said that, it's no longer true, and so you're just relying on human memory, which I think is well shown to be pretty fallible at this point. And so being able to codify your infrastructure is really important, because with something like Terraform, what happens is you hire somebody and that new person says, okay, how does the infrastructure work? How does the networking work? How do things communicate? And the more senior people can say, just look at the code. We don't have to tell you anything. That person, the more senior person could quit, something could happen, and all the knowledge is still there. You don't need to rely basically on more senior people to get your more junior people up and running. And that's super important, mostly from being able to grow, because the number of applications and servers that we're deploying is just growing at an insane pace, and relying on just manual sort of education isn't enough. We really need to allow people to self-educate on this stuff, and Terraform and infrastructure as code does a good job of that. And so back to the configuration syntax though, the syntax that I just showed you, and I'll show you on the next slide, is called HCL. It stands for the HashiCorp configuration language. It's actually a language we use across all our tooling, or most of it. And it's been a few years now since HCL's existed, and our community, 99% of the community thinks it's actually a very pleasant way to work with our tools. However, since it is our own configuration format, we do include complete JSON compatibility with it in every case. So if you want to write JSON, you could do that, although the community accepted best practice, almost all the Terraform you're going to see is going to be written in HCL. The JSON nowadays is very important, and it's a first-class feature. It's not a second-class sort of thing. but it's primarily used for machine-generated configurations. So it lets machines like CIs and other things actually generate Terraform configuration, which is pretty useful. So let's go back to this example. This just shows you how it's text, so it's easy to see diffs. So if someone committed a change to your infrastructure using something like Git, you could just really easily see the change. You don't need to dig in too deep to understand what happens. And another important point here is that Terraform configuration only represents the end state of what you want to achieve. You don't tell Terraform how to get there. You don't give Terraform a set of steps. You just tell Terraform what you want your infrastructure to look like, and Terraform's job is to make it so. And we'll talk more about how the nuance there later. So the syntax really easily, the first part of it in this bold here, resource, is just a keyword that says we're defining a resource. A resource in Terraform is anything with lifecycle attached to it, so create, destroy, update. It's something that's managed. So in this case, the resource is an AWS instance. The second part is the type of thing you want to manage. So you could also put an ELB here, Route 53 record, etc. The third thing is a unique name, and this name is just for Terraform. This AWS doesn't see this name. It doesn't map to any specific parameters in AWS. This is just for you to reference and understand within Terraform itself. So we name it, in this case, web. This has to be unique. So if you created another AWS instance, if you wanted to manage two, you couldn't name that one web as well. You would have to rename that to web 2 or anything else, pretty much. And then finally, these things on the inside are the attributes. So attributes are the configuration for the type. So this will differ for each type. So if I was configuring an ELB here, it wouldn't have an AMI option, for example. It's different. So in this case, we set some types that tell Terraform how you want the AWS instance created. And again, to reiterate, this only includes the end state, what you want it to be, not what it is today. And then the last feature is what we call interpolations. They're ways to reference attributes of other resources within Terraform. So for example, if we're managing an ELB, one of the attributes there is to specify the instances that the ELB is load balancing to. And that's a list of instance IDs. And one way we could do that is, if we wanted to load balance to that instance that Terraform just created, is to just reference the ID of the instance it just created. We don't know it, until it's created. So by putting this here, Terraform at runtime will fill in that value and make the ELB manage that instance. So the first command that you're really introduced to after writing Terraform configuration is plan. So plan is that feature I talked about earlier, which it shows you what's going to happen. And this is super important, and it's better than just a dry run. So there are some tools out there that provide what they might call no-op modes or dry runs, and Terraform plan is that, but more, because what you could do with Terraform plan is also save the plan, and if you save the plan, you could run Terraform with that plan and tell Terraform basically you only do this. So usually a dry run is what a dry run is basically saying in other software, not Terraform competitors or anything, just like other classes of software. What a dry run usually says is, if you ran this software right at this moment for this state of the world, this is what would happen. But the state of the world changes, and if you run it a second from now, or a minute from now, or a year from now, it's probably going to do something different. So with Terraform, by default, a plan is a dry run, but you can also save a plan, and that gives you the additional guarantee of telling Terraform to do only something and don't do anything else, even if the state of the world changed. And this becomes very, very important as you manage sort of production critical infrastructure with Terraform. And really the problem this is solving is, prior to Terraform, people had to just guess sort of what was going to happen. So early on when we released Terraform, we'd go to some big potential users that wanted to learn about it, and they would have a team of 20 or 30 people managing their AWS infrastructure, but there was one or two gatekeepers to the whole thing that had, I like to call them sort of the oracles of the infrastructure, because they had the sort of knowledge where if you showed them what you wanted to do, they would have to sort of divine what the ultimate rollout effect of this change would be. Like, would changing the AMI of this instance trigger a new, a change that's necessary in the ELB to point to this instance? Does that trigger DNS changes? They would have to think of this full rollout. What Terraform Plan actually does is alleviates this. So that company actually, that was a real example, and that company actually adopted Terraform and was able to no longer have gatekeepers. Everybody is able to deploy to production as long as the plans look good. So, I mean, there's still people approving the plans, but a larger number of people could do it. So this gives more junior people more power, but safely. And so a plan, when you output it, is formatted similarly to sort of like a diff. There's colored symbols next to it to indicate what it means. So a green plus means that a resource will be created. A red minus sign means the resource is going to be destroyed. A yellow or orange tilde means that a resource is going to be updated in place. So it's not going to be destroyed to be updated. We could update it in place. That still might mean there's downtime depending on the type of resource you're updating, but at least we don't need to destroy it. And then a minus / plus, again in yellow or orange, indicates that a change requires a resource to be destroyed and then recreated. So an example here might be if you're updating an AMI on an AWS instance, you can't do that in place. To update an AMI on an instance, you have to actually create a new instance. So that would be a minus / plus operation. So on that configuration we just had, here's sort of what it might look like if you ran Terraform Plan. In this case, we don't have any instance yet. So what it's showing you here is that it's going to create with the green plus. It's going to create that instance. You could see all the attributes that it's going to have. Some of them are known. So the AMI and the instance type we specified. So it just tells you that's what it's going to be. But there's also a number of other things that Terraform knows that it will know, but that it can't know until it's actually created. So things like block devices or IP addresses and so on. Those things Terraform knows will become available after the instance is created. And the reason why Terraform knows this is so that other things like ELB or DNS can reference those things. So your DNS resource can reference, for example, the public DNS of a non-created instance because Terraform can guarantee that that will be available and order things properly so that your DNS record's only created once that is available. So once the plan looks good, the next command you hop into is Terraform apply. And what Terraform apply does is actually executes those changes to reach your desired state. So everything you see in the plan, Terraform apply actually performs. So the plan does, it's important to just reiterate that the plan does not impact your infrastructure. A plan never ever performs changes to your infrastructure. It's purely read-only. It might query your infrastructure to see what its current state is, but it never ever performs a write or a change operation. Terraform apply, on the other hand, executes all of those changes. And so what Terraform apply does is it determines the ordering. So I don't think I have the slides to show, but in that previous example with the ELB that referenced the instance, that actually tells Terraform the ordering that's necessary. So I'm actually just going to go back to it. So in this case, for example, you'll notice that we didn't explicitly specify any ordering of the instance must be created before the ELB, but Terraform does consider that interpolation there being an explicit direction to do that. So because that interpolation is there, Terraform knows that the instance must be created before the ELB and does the ordering properly. In this sort of simple example, it's easy, in a manual fashion to know that you must create the instance for the ELB. What gets really interesting with Terraform is when you start managing more and more complex infrastructures and doing more and more complex changes, understanding sort of the ordering necessary to make things safe, it becomes more and more difficult. And it's really nice actually to run a Terraform plan and just see what's going to happen, know that Terraform's going to handle the ordering for you properly. But again, you can verify that with the plan. And also it parallelizes things. So with this example, if we were creating 2 AWS instances, but we were only putting web in the ELB, it would create both the instances in parallel and also create the ELB before maybe the second instance was ready because it doesn't need it. So Terraform will parallelize as much as possible. And this is super important for cloud resources because cloud resources are fast, but you don't get them instantly. They take seconds, dozens of seconds, minutes. Some things like RDS, could take multiple minutes because they're pretty complicated. And so it's really important that a tool be able to do multiple things in parallel. in order to just get as much done before the cloud control plane can respond. And then the last thing that's also just critically important for the tool is to be able to handle and recover from transient errors. So clouds are complex things, and if you're building, an infrastructure that has 500 or hundreds, dozens even of resources, it's not unusual to just get a transient error. Just a temporary error happens, or maybe it might be on Amazon's side, but a lot of times it might be on your side. If you're creating infrastructure that takes 10 minutes to come up, it's possible in those 10 minutes that your internet cuts out or something just happens. And because of this, you need to be able to handle this safely, and Terraform does. So actually, one of our sales engineers, when demoing Terraform, one of their, I don't know if they still do it, but one of their favorite things they used to do was start a reasonably long, multi-minute Terraform apply, and then in the middle of the Terraform apply, actually just turn off their Wi-Fi. And the really fun thing about this is Terraform will error out and say that it can no longer communicate with Amazon, and it exits. But then when you turn on your Wi-Fi again and rerun Terraform, it completes the operation. It doesn't create duplicate resources. It knows what it did already, and it sort of completes it. And being able to handle from these transient errors, and that's a good example of being able to handle these transient errors. So I recommend when you're just getting started with Terraform to just try things out like that in order to build confidence and understand how Terraform behaves. But in the face of error, it tries to complete as much as possible, exits, and then when you run it again, it just completes what it needs to reach your end state. So here's an example of what Terraform apply looks like when you run it. It just says what it's creating. So this is, again, our example we just had. It shows you the instance it's creating, shows you the attributes that it got. It has some nice output about letting you know if things are still happening. Again, with cloud resources, it's very common for things to take a while. And so instead of staring at a completely non-interactive screen, Terraform lets you know every 10 seconds what's still going on. And then at the end, it tells you the summary of what it did, how many things it created, how many things it changed, how many things it destroyed. And yeah. So Terraform apply gets you from your current state to your target state. And if you remember, I've said a few times that your configuration only represents your end state of what you want your infrastructure to look like. It says nothing about what your current state is. And it's Terraform's job in order to figure out that diff, to figure out what's going on currently and what changes do I need to get there. And so when it inspects this, if possible, it'll just update existing resources when it can. When it can't, or if they don't exist, it will create resources. So here's an example where if we take that example we just did, and in this blue here, we added some tags. So we just made a change. We already applied it once. Now we're just making a change to the tags. And tags don't require creating a new resource. You could add tags after a resource, after an instance is created. So if you run plan, you could see that. The plan shows you the squiggly line, which means that it's going to be updated in place. And then the plan only shows that the only things that's changing are these tags. So you can see that the number of tags is changing from 1 to 3, and that the 2 tags that are being added are foo and zip. And you can see even the summary, nothing's being created, nothing's being destroyed, but one thing is being changed. And then when you apply it, you can see that instead of creating, it's now a modification operation, and it does it in place. So in this case, it didn't destroy your old instance. It didn't incur any downtime or anything. It just did this all in place. And you could see that by the way it ran. And this is again, in this small example, really easy to say, a person could just do that. It's really not complicated. But when you're changing the end state of a complex infrastructure, it's really not uncommon for a plan to have dozens of changes, dozens of additions, dozens of destructions. And in those scenarios, it's really hard to reason about the ordering things need to happen, or sort of the effect of it. And one of my favorite examples of this one, and this wasn't an AWS example, but someone was using a cloud provider where they requested an instance, and one of the things that their company would do would use Terraform programmatically to resize the instances, the memory allocation on the instances. And this required destroying and recreating those instances. And they ran their business on this and they did other things. But what was really cool, what makes the story really cool, is at some point that cloud provider added the ability for memory change to be an in-place operation and no longer require downtime. You could actually dynamically change the RAM allocation on a machine. And because this company, is focused on other things, they didn't keep up with sort of the news and this sort of thing. But one day they updated Terraform, and suddenly their applies were doing in-place updates instead of full resource destruction creation. And they just sort of got that for free. And that's one of the really important properties of Terraform that I just can't state enough, which is that with Terraform, you get the combined infrastructure knowledge of the entire community to make Terraform work. So you don't need to keep up with the latest changes of how things work. Sometimes you just update Terraform and it just does things better. And that's a pretty cool thing to get. And then the last command I'm just sort of going to cover here is Terraform destroy. It's really simple. It just destroys everything that it created. So it only touches the infrastructure that it managed itself. It doesn't touch anything else you have in your infrastructure. But it's a really nice way to clean things up. It makes it really easy to use Terraform for things like staging environments or development environments, and just tear them down when you're done. And Terraform destroy has all the same properties as apply, with handling partial errors and so on. So, if you're running destroy in something like a CI to clean up, it's really nice because if it fails, you just rerun it, and you just rerun it until it succeeds. And it's not common to have failures like that, but it's nice to know that you don't have to think about it. You just run it until it exit codes 0, and you're sort of good to go. Okay, so that was sort of like a whirlwind introduction to Terraform, and Terraform's, like many tools, is something that is really easy to get into. I think you know enough at this point to easily sort of get started with Terraform. But it has a lot of depth too, and due to sort of the time constraints of the webinar, I can't go too deep. But something I wanted to talk about is, okay, you have this basic knowledge. How do you start applying it to a realistic example? And this is going to be a very high-level sort of workflow example of what you should do when you're getting started with Terraform. The examples I show you here aren't going to be runnable exactly as is or anything, but they should give you, enough breadcrumbs to get to where you need to go. And so going back to this example here that I showed earlier in the webinar, this is a really standard web application deployment, like I said. When you start using Terraform, you'll start to see these things sort of like this. And with this example, what's actually happening here is that the purple circles are resources, and then the arrows between them are the interpolations. And when you start thinking about your infrastructure, very quickly after you start using Terraform, this is how you're going to start seeing things. But it's a really useful way to see things. So going back to here, the purple circles are the resources, and the arrows are the interpolations. So let's get started turning this into a terraformed infrastructure. And so what's really important about adopting Terraform is that you don't have to go all in. Terraform isn't useful only if it's completely managing your infrastructure. It could manage just a partial part of your infrastructure and still be very useful. So that's the best way to adopt it, is identify something, especially when you're getting started, just identify something that's easy to automate, low risk, and just start there. So in this case, I put a purple box around what is probably a safe thing to automate in every web application, which is sort of the web server tier. The web server tiers are usually stateless. They could come up and down, and load balancers handle routing to them only when they're healthy and draining when they're not. And so they're usually a pretty safe way to get started. So if we're getting started here, what the box is around is pretty much just purple circles. There's no arrows fully contained in the box yet. So we just have to create a number of resources. So that might look like this. So we create the resource. It's an AWS instance type. It's part of the web tier, so we'll just name it web. Remember, that's just an internal name for us. And then we specify a number of attributes. The one thing here that we didn't talk about, that I will now, is this count thing. And so every resource in Terraform can specify a count, and this is a meta parameter, so it's a parameter to Terraform and not to AWS itself. And what Terraform does with this is just duplicates this thing exactly that number of times. So in this case, we're saying count equals 4 because in that diagram I just showed you, there was 4 instances. So it might just look as simply as this. In the diagram, actually, like exactly, it's using an autoscale group. But to get started with Terraform, you might just start with this and work your way up to that. So we're just going to show this AWS instance without an autoscale group as an example. So once you have that in place, the green box shows us what's done. We've now sort of terraformed those 4 things. And now we can think, what's next? Like, what's the next easiest thing? And you can kind of go any direction. But in this case, this load balancer looks like a good place to go. And so if we want to do the load balancer, we're now looking at this purple circle to manage the load balancer, but also the arrows that are pointing to those web servers. We need to be able to reference those instances somehow. So here's how that might look. We add an ELB resource, and then for the instances, we just reference all of them. So this, again, is kind of new syntax. I've shown you interpolations of referencing one, but when you have multiple, you could use the star syntax that's in here to say I want all of them. So in this case, if we change the count of AWS instance, for example, from 4 to 5 or 4 to 3 or 4 to 40, after doing all that, Terraform would update your ELB with all of those instances IDs. And so that automatically creates those 4 arrows that we had. And so now at this point, you would have sort of a green box around all these things, and you'd be automating all of this with Terraform. And at this point, you sort of just rinse and repeat. You choose what you want to automate and what you don't want to automate. And really, even for people that use Terraform really, really heavily, it's not uncommon for people to just feel comfortable with a few things to just still manage manually for whatever reason. Maybe it's just difficult to automate. Maybe they have a really good system in place that doesn't require Terraform. You don't need to apply it to 100% of your infrastructure, and that's one of the reasons it could be so great. So just rinse, repeat. And so I want to give you some next steps, since I know this is a very surface level sort of talk. So I want to give you some next steps to just sort of guide you towards, if this was interesting to you, what you could look at next in order to learn more about Terraform and implement it successfully. So there's a few features that you should definitely look at. You know all the basics, and so these features wouldn't be scary to look at, but variables and outputs are a way to parameterize your Terraform configuration, which becomes important pretty quickly, so those would be important. Interpolation functions, so you saw interpolations like referencing the ID and stuff. Terraform ships with a really rich library of probably 50 or so interpolation functions that you could actually call to mutate some of that stuff. So this comes from really basic things like turning things to all lowercase to more advanced things, but like actually manipulating things like CIDR blocks and network addresses and parsing IP addresses, which becomes really important with infrastructure. So I recommend taking a look at the interpolation functions. It's just like a standard library that comes with Terraform. Modules are a way to encapsulate your configuration so that you don't need to repeat yourself. So and they're shareable. So for example, you could wrap your company approved way to manage VPC layouts. You could wrap that in a module and tell everybody, if you ever need a VPC, use this module. And users of the module wouldn't have to really know the details of what kind of CIDR block to use, what size space, how many subnets, how do we configure NATs, how do we configure routes. You don't need to know any of that. You could just say, I want a VPC, and then the module would create it for you and give you sort of the relevant information like security groups and the ID of the VPC and things like that. So modules, they pop up relatively quickly once you start using Terraform. And then the last thing is remote state. So remote state is a way to basically collaborate on Terraform more efficiently. And I'll just sort of leave it at that, and you could take a closer look. But these are the things that you probably want to look at next. And then the resources that are available to you is the project website. So the project website has docs covering everything. So the project website is going to be indispensable as you use Terraform as reference material. There's a third-party community GitHub organization called Terraform Community Modules, which actually we're sort of gearing up to become more involved in. But this is just a community thing that spun up that shows it's a really good way to look at example Terraform modules, and they're pretty high quality. So take a look at those. Google's your friend. So especially in the past 6 months, Terraform has just been on a really rocket ship level of adoption, and so there's a lot of blog posts out there that cover how to use Terraform. So don't be afraid to Google things. You'll probably find an answer. As part of that, I should mention that Terraform also has sort of official community avenues. So there's a Gitter channel for real-time communication, which has a couple hundred people in there on average, and I hang out in there and see it's pretty active. And then there's a mailing list, and the mailing list is a good way for, if you don't want an answer now, send it to the mailing list, and you'll probably actually get more people viewing your thing on the mailing list than you will in the real-time chat. So if you go wait a little bit, the mailing list usually gives you very high-quality responses too. HashiCorp as a company also does various events sort of like this. We do user groups. We also do trainings as well if your company wanted that. And then the last thing that I want to mention is books. There's actually, just in the past month, we've gone from 0 Terraform books to 2 Terraform books. So terraformbook.com is written by someone in the community and is actually available now. So you could take a look at that. And then actually just today, so I didn't even update the slides. I didn't even know until today. But just today, O'Reilly announced that they have an early pre-release version of a Terraform book as well. So those are both pretty up to date with the latest version of Terraform, and you can check those out. And then the last thing I want to show is just sort of like just a screenshot of the website. Of the website's documentation. On the main repo, sort of addressing the multiple modules. So I will mention that this is actually a use case that we have planned sort of solutions for Terraform 0.9, which is going to be early next year. So right now you could totally do it, and we have customers that are managing this. It's just a little more manual than we would like. And then in the future, we're actually going to give you a bunch of workflow tools to manage this. So hope that helps.